Our problem is from GATE 2021 mathematics paper, question number 46. The problem given is, let R the region given by the complex numbers z equal to x plus iy in C such that 0 less than x less than 1 and minus 11 pi less than y less than 11 pi and gamma be the positively oriented boundary of R. Then the value of the integral 1 divided by 2 pi I times integration over gamma e to the power of z divided by e to the power of z minus 2 dz is dash. So it is asked to calculate the value of this integration. And to solve this problem, the NPTEL reference is Module 1, Lecture number 2 of Advanced Complex Analysis Part 1. The title of the lecture is The Argument Principle, Closures Theorem and the Fundamental Theorem of Algebra by Dr. T.E. Venkatabalaji. He is from Department of Mathematics, IIT Madras. Even you can watch this lecture using this YouTube link. Now coming to the solution, by using the argument principle, firstly let me write what is given. It is given the region R, given that z equal to x plus iy in C such that 0 less than x less than 1 and minus 11 pi less than y less than 11 pi. Then it is asked 1 divided by 2 pi I times integration gamma, the function f is given as e to the power of z minus 2 dz. The value of this integration we have to calculate. Since we have the argument principle, which states integration over C, any closed curve C, f dash of z divided by f of z dz is number of zeros minus number of poles. That is n as the number of zeros of f inside C and p is the number of poles of f of z inside C counted with multiplicities. So now to solve this problem, we assume or we let f of z is equal to e to the power of z minus 2. Then we have f of z as e to the power of z. So by using the argument principle, we can directly see the integration e to the power of z divided by e to the power of z minus 2 dz is given as n minus p, where n is the number of zeros of the function f of z, and we assume the function as e to the power of z minus 2 inside gamma, since the closed curve is given as gamma, and p is the number of poles of f of e to the power of z minus 2 inside gamma, and we can see the function e to the power of e to the power of z minus 2 is entire, and hence it does not have any singularities, and in particular it does not have any poles in the whole of complex plane. So of course this is with multiplicities, counted with multiplicities. Since we have e to the power of z minus 2 is entire function that is analytic in the whole of complex plane, entire function in C, so it does not have any poles. In particular, it does not have any singularities in the complex plane. So we have the value of p as 0. Now coming to the value of the number of zeros of e to the power of z minus 2. Now to calculate the value of n, we let e to the power of z minus 2 equal to 0. Now from this equation, we see the values of z inside the closed curve gamma. How many such points z exist inside gamma, which defines the value of n. From that, we can easily see the value of that particular integration which we need to calculate. Now to solve this, and okay, firstly let me write, or let me draw the curve gamma given by, this is the complex plane, and this is the point 1, this is the origin, this is the midpoint. Let me assume this is 11 pi. So approximately this will be minus 11 pi. Now the curve gamma is given by, so the region R is this shaded region. This is the region R. Now to solve the equation e to the power of e to the power of z minus 2 equal to 0. From this equation, we can see e to the power of z equal to 2. And from this, we can see the value of z as log 2. And by the definement of the logarithmic function, we have this, the value of log 2 can be ln2 plus 2 pi n I, where n runs over all integers. Or even one can see, since the function exponential function is periodic with periods it 2 pi I, sorry, 2 pi n, we can see the solutions of this equation are ln2 plus 2 pi n pi, sorry, ni. Since exponential is the logarithmic function, for each any solution of this equation, when you add 2 pi 2 pi ni, that is also a solution of this equation, since exponential is the periodic function. But the question here is, out of all these solutions, how many solutions does lie in this region R? So for that, by varying the value of n over all integers, we see, but out of all these solutions of e to the power of z minus 2, the only solutions lie inside the region, or let me write inside the contour or curve, inside the curve gamma, or ln2 ln2 plus or minus 2 pi I ln2 plus or minus 4 pi I comma ln2 plus or minus 6 pi I ln2 plus or minus 8 pi I and ln2 plus or minus 10 pi I. And we can see that the value of ln2 is approximately 0.3010, which lies in between the real numbers 0 and 1. So we can see the real part of all of these solutions lie in between 0 and 1, but whereas to lie the imaginary part of the solutions in between minus 11 pi and 11 pi, the only values of such solutions, the only imaginary values of such solutions are plus or minus 2 pi I, so 2 pi, and plus or minus 4 pi, plus or minus 6 pi, plus or minus 8 pi, and plus or minus 10 pi. And in total, now we can see these are the only solutions which lie inside the curve gamma, and which are the solutions of the equation e to the power of z minus 2 equal to 0, and which denotes the number. So n is 11 and p equal to 0, since e to the power of z minus 2 is entire. Hence, or therefore, the integration e to the power of z divided by e to the power of z minus 2 dz over the closed curve gamma is given as n minus p, which is nothing but 11, where 11 is the number of zeros of the function e to the power of z minus 2 inside the curve gamma, which is by the argument principle. Thank you.